I think I just started the recording.
So I was going to say, I think there is a recording now.
Yeah, but I mean, this is just if you feel okay with that. Otherwise,
yeah, no, I was what's her name? Constanze. She told me that you usually record the talks. So
yeah, so but again, completely sort of.
Yeah, no, it's fine. It's fine. You can definitely record.
Yeah, because sometimes there's administrative things that prevent all of us. In fact, some of us today are not here because of that. So we'd like to have the record.
Yeah, that's fair enough.
All right, it's 14:31. I think we can start. Our today's speaker at the LUCI seminar is Ina Jäntgen, who is a postdoc at the Munich Center for Mathematical Philosophy. Ina did a PhD at the University of Cambridge, and she specializes on philosophy of science, formal epistemology, and decision theory. And today's talk will be about standardizing mean differences from a rational choice perspective. Ina, virtual floor is yours, and you said we have around 40 minutes, right?
Yes. Yeah.
Okay. All right. Thank you.
Oh, that's okay. Yeah, thanks a lot for having me and for the invitation. One thing to show it, I did put a link to my slides. So if anyone wants to go ahead and look at that, feel free to do so. So thanks for the invitation. I'm excited to be here today. In this paper, I'm interested in focusing on areas of science where scientists test treatments or interventions in an effort to inform decision-making. And when scientists do that, they typically also measure and report what is known as an effect size of a tested treatment. That is a measure of how effective a tested treatment is, how large the observed effect is. And the resulting effect sizes are then often used to inform decision-making. And in today's talk, I focus on a widespread practice of using so-called standardized mean differences to express how effective tested interventions are, and to then report the effect size or the effectiveness of tested interventions to decision makers. And the problem I want to argue for in today's talk is that using standardized mean differences to inform decision making actually risks not facilitating rational decision making. It omits information that a rational decision maker would care about learning. So that's the negative part of the paper. The more positive part of the paper is that I'll also show that there are some circumstances, some scenarios in which we can avoid the risks. So in which standardizing mean differences never strips away information that matters to rational decision making. So overall, I then tell a cautionary story about standardizing mean differences. So that's all quite abstract. So to get us started, I wanted to introduce what a mean difference is and what a standardized mean difference is. And I want to do that by focusing on an example. So consider the study here in which researchers tested the effectiveness of a collaborative care program for reducing depression severity in cancer patients. So this collaborative care program is basically a set of different psychological interventions that are delivered by trained nurses, and these interventions are kind of incorporated into the usual cancer care. And so in this study, researchers were interested then in testing whether or not this collaborative care program would reduce depression severity. So what they did is they divided their study participants into a treatment group, which all were treated with the collaborative care program, and a control group, which just proceeded with the usual cancer care. And then they measured depression severity in the treatment and control group. So in this particular study, they measured depression severity by using what is known as the symptom checklist measure of depression. So that's SCL20 measure of depression. So this depression measure asks people to rate the extent to which they experience different symptoms of depression on a scale between 0 and 3, and then we take the average of all the different items the patients are asked about, and that's the resulting CSL score. So the checklist score, which ranges between 0 and 4, where 4 signifies the most severe depression. And just for simplicity, I will speak about the checklist scores, but I have the CSL20 scores in mind. Okay, so then researchers ended up with a checklist score for all the people in the treatment group and all the people in the control group. And based on that data, they then drew an inference as to the treatment, the collaborative care program being effective at improving depression or reducing depression severity. But typically in this context, researchers want to not just make a statement about whether or not a treatment is effective, but also about how effective a treatment is. That is, in this context, how much does the treatment reduce depression severity? And that can be done using the so-called mean difference. So the mean difference is defined as the difference in the expectation or average or mean outcome in the treatment and control group. So in this particular study, the mean difference was minus 0.38 checklist scores, and that means that on average, the treatment reduced people's depression severity by 0.38 checklist scores. Here's an illustration of the mean difference. It's the difference between the means, which is the peak of these distributions. Now, the mean difference is one widely used effect size measure, but another widely used effect size measure is the so-called standardized mean difference, and that's defined as the mean difference divided by the standard deviation in the population of interest. So just a brief reminder, the standard deviation, roughly put, measures how spread out the distribution is. So if you contrast the control group distribution here with the treatment group distribution, you'll see that the control group distribution is more spread out around the peak, the mean, than the treatment group distribution. And that signifies that the control group distribution has a higher standard deviation than the treatment group distribution. So the standardized mean difference is defined as the mean difference divided by the standard deviation in the population of interest. Typically, that's estimated with the control group standard deviation. So in this particular study, the standardized mean difference was, for instance, minus 0.62. Now, of course, there is a question now of what this number means, how to interpret the standardized mean difference. And I will return to that in just a moment. But for now, I want to emphasize that these effect sizes, both the standardized mean difference, but also the mean difference, are really widely used to influence and inform evidence-based decision-making in areas, for instance, like medicine, psychiatry, education research, economics, but also other social sciences. So in all these areas, it's the case that scientists measure and report effect sizes to inform decision makers, and they're often indeed demanded to do so by major journals and research organizations like the American Psychological Association. It's also the case in all these areas that institutions and organizations which produce guidelines for decision makers based on scientific evidence rely on these effect sizes. So for instance, in the UK, the National Institute for Health and Excellence writes clinical guidelines to guide clinical practice, and these guidelines heavily rely on these effect sizes, the standardized mean difference and the mean difference. And it's also the case that in these contexts, there are major public institutions which rely on these effect sizes to make public decisions. For instance, in the US, the Food and Drug Administration, the FDA, relies on such effect sizes as the mean difference and the standardized mean difference to make drug approval decisions. So in short, these effect sizes widely influence decision-making. And in particular, in contexts in which researchers are uncertain about how to compare and interpret mean differences, it's frequently the standardized mean difference, not the unstandardized mean difference, that is used to inform decision makers. I will explain the rationale for standardizing in detail in just a moment, but for now, let me emphasize that I'll try to argue today that there's a problem with this practice of relying on standardized mean differences to inform evidence-based decision-making. And that problem is that insofar as the most salient piece of information that is conveyed to a decision maker, insofar as that's the standardized mean difference, that risks stripping away information a rational decision maker would care about learning compared to providing that decision maker with the underlying mean difference. And that's about standardizing mean differences, risk stripping away information rational agents care about learning. As I already said, there are some scenarios in which we can avoid that risk. Also, I'll argue. And I should say that these scenarios will involve some of the assumptions that are often made in interpreting standardized mean differences. Okay, so these are the two main claims of the paper. Here's how I'll proceed. So I already motivated the talk. I will now explain why we standardize mean differences. And then I'll articulate the risk of standardizing mean differences, how to avoid the risk, and also then end with the path forward. Okay, so why standardize mean differences? To see that, I want to consider an example of how a mean difference might influence someone's decision. So consider this example here. Imagine you're a doctor and you have a patient who has lung cancer and also suffers from clinical depression. And now you can choose between two possible interventions. One is to enroll the patient in the collaborative care program that I already spoke about. And the other option is to enroll the patient in a supervised physical exercise program. And you learn from studies that both of these interventions are effective at improving depression severity. And you also learn the effect sizes of these interventions in terms of their mean differences. So we've already encountered the mean difference associated with the care program. That was minus 0.38 checklist scores. And let's say that the mean difference of the exercise program from a study that tested the exercise program is minus 2.2 on the so-called HATS-D score scale. So the HATS-D score is the Hospital Anxiety and Depression scale. So that's the HATS scale. And the HATS-D score would then be the subscore for depression. So that's the HATS scale. The HATS scale is another standardized measure used to measure depression severity. It scales between 0 and 21, where 21 indicates the most severe depression. I'll just speak about HATS scores for simplicity. You now might be uncertain, how does the mean difference of the care program in terms of checklist scores relate to the mean difference of the exercise program in terms of HATS scores? In particular, does a reduction of 0.38 checklist scores represent a bigger or smaller reduction in depression severity than a reduction of 2.2 HATS scores? Insofar as you are uncertain about the relationship between these mean differences, you are in good company, because that's exactly the kind of uncertainty that would motivate researchers to rely on the standardized mean difference rather than the unstandardized mean differences. So let's unpack this uncertainty a bit more. More specifically, researchers may on the one hand be uncertain how to interpret a particular mean difference, because they may be uncertain about how the measurement scale relates to the measured property. So for instance, you might be uncertain what minus 0.38 checklist score represents about a reduction in depression severity, because you might be uncertain how checklist scores represent depression severity. On the other hand, researchers may be uncertain about how to compare mean differences measured on so many different scales. So how does the reduction of 0.38 checklist scores relate to the reduction of 2.2 HATS scores? That's an uncertainty that comes from being uncertain about how the checklist and the HATS scores relate to each other in terms of depression severity. This latter comparative problem is quite prevalent in the context of conducting meta-analysis. So when you're trying to take evidence from different studies and combine that evidence, but the different studies measured presumably the same outcome of interest on different scales. So in short, researchers may be uncertain how to interpret and compare mean differences. And both of these concerns are frequently expressed in the statistical and methodological literature. But they're typically not explained more in detail. But of course, as philosophers of science, we should do that. So we should unpack what these concerns with interpreting and comparing mean differences really amount to. And in the paper, I give a detailed account of what these concerns amount to, relating it to the literature on philosophy of measurement. So I won't have time to talk about that in detail here, but just very briefly, I argue in the paper that concerns with interpreting and comparing mean differences, on the one hand, come from being uncertain about what property we're measuring, and in particular, whether or not we're measuring the same property in different studies. So for instance, do the checklist scores and the HATS scores represent the same aspect of depression severity or not? On the other hand, measurement uncertainty or concerns about interpreting and comparing mean differences can come from uncertainty about what type of scale we're dealing with, or the relationship between token scales. So to understand that, I wanted to give you a brief reminder about what we mean by speaking about different types of measurement scales. So typically, we distinguish between measurement scales that are ordinal, those that are cardinal, and those that are ratio scales. So brief example, suppose we have two patients. One has a HATS score of 10, and the other patient has a HATS score of 5. And let's say that HATS scores represent depression severity on an ordinal scale. That would mean that the numbers on the scale merely represent which object satisfies the measured property more. So if HATS scales measure depression severity on an ordinal scale, then we could say that Tom is more depressed than Lily, based on the Tom having a HATS scores of 10 and Lily a HATS scores of 5. But we couldn't say more than that. We couldn't say Tom is much more depressed than Lily or twice as depressed as Lily. By contrast, for cardinal scales, we can make statements about how much more an object satisfies the property compared to another. So if head scores measure depression on a cardinal scale, then we could say, based on Tom having a head scores of 10 and Lily having a head scores of 5, that Tom is much more depressed than Lily, right? And finally, if you're dealing with a ratio scale, we can make statements about how many times more an object satisfied the measured property compared to another. So if head scores measure depression on a ratio scale, then it's meaningful to say Tom is twice as depressed as Lily based on Tom having a head score of 10 and Lily one of 5. Okay, so in short, what measurement scores represent about the measured property depends on what type of scale we're dealing with, whether we're dealing with an ordinal, a cardinal, or ratio scale. Typically, we call cardinal and ratio scales quantitative scales, so sometimes I'll speak about quantitative scales, and that just means I'm speaking about ratio or cardinal scales, not ordinal ones. Note now that if we are dealing with a property that is measurable only on an ordinal scale, then we cannot meaningfully speak about one group satisfying that property on average more, right? Because to speak about an average, we would have to speak about different objects satisfying that property by some amount more or less. But if it's a property that is only measurable on an ordinal scale, then we can't do that. We can't speak about amounts of that property. So for instance, if say depression severity is only measurable on an ordinal scale, then we cannot infer from a group having a higher average head score to that group being more depressed on average than another group. Okay, so that's so basically in a slogan, if a property is only measurable on an ordinal scale, then we can't meaningfully speak about averages with respect to that property. And that, of course, relates then back to interpreting and comparing mean differences, right? Which are, after all, claims about differences and averages. So, for instance, if you are, to go back to this now, so uncertainty about how to interpret and compare mean differences can then come from being uncertain about whether we are dealing with an ordinal scale or a quantitative scale. If it's an ordinal scale, then a mean difference may be meaningless. If it's a cardinal or ratio scale, it may not be meaningless. Okay. And then finally, measurement uncertainty can also come up from being uncertain about how different scales relate to each other, even if you're certain they're, say, both cardinal scales. So even if you are certain that the checklist scores and the head scores are both cardinal scales, you may be uncertain about how much depression one score shift on the checklist scale represents compared to a one score shift on the head scale. And that could then give rise to problems and uncertainty about how to compare and interpret the mean differences. Okay, this is just a very brief run through to the kinds of measurement uncertainty that really gives rise to the challenges of interpreting and comparing mean differences. Now, a lot more could be said about this, but I now want to move on and ask, well, why does standardizing help? And one thing to be clear about is that nobody thinks that moving towards standardized mean differences allows us to now somehow solve measurement uncertainty. Rather, the idea is that standardizing allows us to convey how effective an intervention is despite currently facing measurement uncertainty. So here's how it does that. There are basically various interpretations of standardized mean differences in the literature. I'll give you 3 prominent ones just to give you an idea of how people think about standardized mean differences. So one interpretation starts from assuming that the standard deviations in different studies express the same amount of depression severity or of a measured property. So for instance, the standard deviation of 0.61 checklist scores and the one of 2.35 head scores both represent the same amount of depression severity according to this assumption. And if that assumption holds, then of course we can just straightforwardly compare the standardized mean differences. We can say that the reduction of a standard mean difference of minus 0.93 represents a bigger reduction in expected depression severity than one of minus 0.62, right? Another interpretation of standardized mean differences relies on this kind of more technical assumption that the measurement scores all follow a normal distribution with the same standard deviation given the control and intervention. So if that assumption holds, then we can actually compare the standardized mean differences as representing the overlap of treatment and control group distribution. So for instance, a standardized mean difference of minus 0.93 corresponds then to an overlap of treatment and control group distribution of 64.2%, versus a standardized mean difference of minus 0.62 corresponds to an overlap of 75.7%. And the idea is that the less the overlap is, the more the effective the intervention, and you're supposed to compare the overlaps across different studies. Okay, so this is supposed to be also a way of conveying how effective a treatment is compared to another. The final interpretation is this one. This one is very common, namely to compare standardized mean differences with other standardized mean differences observed in the context of interest, and in particular with benchmarks. So one common set of benchmark is that the standardized mean difference of 0.2 or smaller is a small effect, one of around 0.5 is a moderate effect, and one of above 0.8 is a large effect. And so in this interpretation, then the exercise program has a large effect, the care program has a moderate effect. Okay, so these are just different ways of interpreting standardized mean differences as expressing something about how effective tested treatments are, despite facing measurement uncertainty. Now, of course, we should ask, are these good interpretations? Are they consistent with uncertainty about measurement, which is perhaps best? And there's a lot to be said about all of that, but for today, I want to bracket all these questions and just take the common practice as face value. And that means that if we are facing measurement uncertainty, we report standardized mean differences. And so going back now to a cancer scenario, in the cancer scenario, more realistically, you would learn the standardized mean differences, not the mean differences of the care program and the exercises. And you'd base a decision on the standardized mean differences then. And what I'm interested in this research is asking, when is that a good idea? In other words, when does reporting standardized mean differences rather than unstandardized mean differences when we face measurement uncertainty actually facilitate good rational decision making? And the problem or the risk is that it doesn't always. So standardizing mean differences, if you face measurement uncertainty, risks stripping away information rational decision makers care about. So I want to unpack that claim now, focusing first on the idea of rational decision making. For the purposes of this talk, I'll just adopt the orthodox theory of rational decision making, that's expected utility theory. So expected utility theory says that an option T is at least as good as another option C, if and only if the expected utility of T is at least as great as the expected utility of C, and you're rationally required to choose an option that's best. So that's quite abstract. So let's unpack it using the cancer example. There, recall you had two options, the care program and the exercise program. And then the expected utility of an option is the probability weighted sum of the outcomes utilities, where outcomes are all the ways the world can go that matters to a decision maker. For simplicity for today in this talk, I want to focus only on cases in which the agent just cares about the property that's measured in a trial. So for instance, you just care about depression severity. That is, we bracket, for instance, side effects of treatments, costs of treatments. That's just a simplifying assumption. I don't make that assumption in the paper, but it makes our life easier for today. Okay, so those are outcomes, and then utility of outcomes. We can think about the utility of an outcome as how desirable that outcome is in choices on uncertainty. So for instance, how desirable are changes in depression severity when you choose between the care program and the exercise program. Okay, and then the relative probability weighting here is of course the agent's beliefs or credences over all the ways the world can go, like the outcomes given the take option. And in the context of evidence-based decision-making, these credences will be informed by scientific evidence, and in particular by an effect size like the mean difference or the standardized mean difference. So let's unpack this a bit more. So suppose you learn a mean difference, and then that mean difference informs your credence about the measured property given the option. Typically, we think that when you learn a mean difference from a study, you'll need to take into account all kinds of reasons for why the mean difference in a study might not adequately describe your decision scenarios. Some of those reasons I list on the slide here. For the purposes of this talk in this paper, I want to bracket all of those and just assume that the mean difference you learn adequately describes your scenario. So for instance, the mean difference in minus 0.93 head scores adequately describes the expected reduction in head scores your patient would experience if they were to be involved in the exercise program. That's the assumption. But of course, what we're not reckoning here is measurement uncertainty. So we are assuming still that the agent may be uncertain about what head scores represent about depression severity. And you can take that uncertainty into account rationally. At least that's what I assume in the paper. I model this as an instance of just standard Bayesian updating, and I measure uncertainty. Now, in the paper, I give a sort of very detailed story about this, but for today, I want to omit most of the details, but briefly give you an impression of what this looks like. So here's standard Bayesian conditionalization, as I'm sure we've all seen it. And then the idea is that we take as hypothesis claims about the chances of the measured property given the tested intervention and compared to the control. So for instance, an example would be a claim about the expected depression severity being lower given the exercise program than given the usual care. Your evidence then in this approach is the mean difference, for instance, or the standardized mean difference, or the effect size you learn. And then the final component is your likelihood, which in general, of course, is your credence in observing the evidence given the hypothesis. And in this context specifically, it will be your credence in how likely the used measurement scale measures the property, such that if and only if the claim about the chances of the measured property is true when we observe the evidence. So for instance, how likely does the head scale measure depression severity such that we observe this mean difference if and only if the claim the expected depression severity is lower given the exercises than given the usual care is true. Now that hopefully, so that captures your beliefs then about the measurement relationship between the head scores and depression severity. I know this is quite quick, but I'm happy to talk about it in the Q&A if people are interested. But basically then you just update by conditionalization, and then you end up with the credence in how likely this claim about the chances involved in the measured property is true, and then you match your credences in the measured property to those posterior credence. Note that measurement uncertainty comes into play at 2 points here. One is what kinds of claims about the chances of the measured property you deem meaningful, including, for instance, whether you think it's meaningful to speak about changes in the average or expected measured property. Because recall, if it's an ordinal property, if you think the property is ordinal, then you wouldn't deem those claims to be epistemically meaningful, empirically meaningful, I should say. The second point at which measurement uncertainty comes into play is in your likelihood. So again, in how likely you think the U scale measures the property such that the claim about the chances of the measured property is true if and only if you observe this mean difference. Okay, so this is then how we take measurement uncertainty into account when we rationally learn. And then the idea is you update your credences when you learn a mean difference, and then you choose whichever option then maximizes expected utility. So that is what it takes to rationally make rational decisions in this context, according to this account. And then recall we are interested in when standardizing mean differences facilitates or fails to facilitate rational decision making. So let's make this question more precise. We will basically contrast two evidential scenarios, one in which you learn the standardized mean difference and one in which you learn the mean difference and the standard deviation. Why contrast these two evidential situations rather than just comparing the standardized mean difference with the mean difference? Well, notice that a standardized mean difference can never provide an agent with more information compared to the mean difference and the standard deviation. Because if you learn a mean difference and a standard deviation, you will always learn the standardized mean difference, right? And so because of that, I think it's of most practical interest to contrast the scenario in which you learn a standardized mean difference with the one in which you learn a mean difference and a standard deviation. Okay. But of course, even though the standardized mean difference can never provide an agent with more information compared to the underlying mean difference and standard deviation, it could in principle provide an agent with just equal amounts of information to make a rational decision, with just the same amount of information needed to make a rational decision. So in other words, the question I'm interested in is, when, if ever, does learning the standardized mean difference provide an agent with enough information, sufficiently informs an agent to identify the same option that agent would choose, the same option that maximizes expected utility, if that agent had instead learned the mean difference and the standard deviation? And if a standardized mean difference provides an agent with sufficient information in the sense, sufficiently informs an agent, then that means it doesn't leave out any decision relevant information. It doesn't leave out information that bears on which option maximizes expect utility, which option is best. So then the standardized mean difference would facilitate rational decision making. But of course, as I've already said, unfortunately, standardized mean differences do not sufficiently inform an agent all the time, according in the sense. So one can show that in choices between two options, learning the standardized mean differences does not always sufficiently inform an expect utility maximizer to identify the same option they would choose if they were to learn the corresponding mean differences and standard deviations instead. Now in the paper, I show this formally, but instead of going through all the details here, I want to give you a brief example, which hopefully also illustrates what I mean by sufficiently informing a bit more. Let's go back to the cancer case. And let's assume, just for simplicity, that the cancer patient and the doctor care about every equal reduction in depression severity equally. So they have a linear utility function in depression severity. That's just a simplifying assumption. Let's assume that the researchers and the doctor face measurement uncertainty of the kind that they can't quite know. They don't really know how to compare the mean difference of the care program and the exercise program. And so they use the standardized mean difference. So the agent learns the standardized mean difference. And let's assume that the doctor is uncertain about how much depression severity these standardized mean differences from the two studies represent. Now, given that assumption, there are, of course, a variety of mean differences and standard deviations compatible with the two standardized mean differences the agent learns here, right? So, for instance, the mean differences and standard deviations, as we've been discussing them, are compatible with the standardized mean differences that the agent learns here. So, for instance, so the mean difference and standard deviations in this first scenario are just exactly the same as I've been using them throughout this talk. And now it can happen that if the doctor were to learn these mean differences and standard deviations, then they might come to expect, given their measurement uncertainty, that the care program has lower expected depression severity, achieves a lower expected depression severity than the exercise program. And insofar as they care about every equal reduction in depression severity equally, they will then think that the care program maximizes expected utility. Notice that the scenario is compatible with a range of attitudes towards the relationship of, or range of beliefs about the relationship of checklist scores and head scores. In particular, it's compatible with the agent's best guess on how the checklist scores and head scores relate, being such that they expect that one checklist score corresponds roughly to 6 times as much depression severity than one head score. So if that's the agent's best guess on the relationship between checklist scores and head scores, then I would come to expect that the care program has lower expected depression severity based on learning these mean differences and standard deviation. Note that I say the agent's best guess, or the agent expects. That's quite different from assuming that the agent is certain, assigns screens 1, to one checklist score corresponding to 6 times as much depression severity than one head score. The agent is not certain like this. The agent is uncertain about the relationship between checklist scores and head scores. It's just their best guess is that it's roughly a 1-to-6 relationship. Okay, so in scenario 1, the agent expects that the care program has lower expected depression severity than the exercises, and therefore the care program maximizes expect utility. But of course, the same standardized mean differences are also compatible with a range of other mean differences and standard deviations. And as you might expect, they're also compatible with a mean difference in standard deviation such that, given the same uncertainty about measurement, the exercises have a lower expected depression severity in the care program, and therefore the exercises will now maximize expect utility for the agent if the agent were to learn these mean differences and standard deviations. So all that's changed between scenario 1 and 2 here are the mean difference and standard deviation of the exercise program, and keeping the same measurement uncertainty as before, the agent now thinks that the exercise have lower expected depression severity. Okay, the point is, of course, that if as an agent you just learn the standardized mean difference, you don't learn whether you're in scenario 1 or scenario 2 or any of the other compatible scenarios, scenarios compatible with the standardized mean differences. And so you don't learn which option would maximize expected utility if you had learned the underlying mean differences and standard deviations. In other words, the standardized mean differences here do not sufficiently inform you. They leave out decision-relevant information. And that's the risk of standardizing that I'm concerned with in this paper. Of course, I've just given you one scenario, and I just want to emphasize that one can get also failures to sufficiently inform an agent without making this assumption that an agent is uncertain about how big the standard deviations are. So this isn't that necessary. But of course, the question now is, what should we do about this? And one response would be to say, let's just give up standardizing. Let's just never standardize mean differences. Now, I don't want to spend too much time on this, but I'm happy to chat about it in the Q&A. I basically think there are good methodological and cognitive reasons to resist this response, to at least not always give up on standardizing mean differences. And those reasons motivate me to ask, well, can we ever avoid the risk of standardizing? Can we identify scenarios in which standardizing a mean difference strips away no decision-relevant information, never omits decision-relevant information? And it turns out we can. So in the paper, I showed that there are classes of scenarios in which, at least for some marginal agents, standardizing mean differences never strips away information they care about. Now, I won't have time to discuss these in detail here today, but I just want to illustrate to you how they connect to the kinds of assumptions people make in interpreting and comparing mean differences. In particular, I will call first this interpretation of standardized mean differences, in which we assume that the standard deviations express the same amount of depression severity. Now, if that assumption holds, then actually one can show that for many rational agents, or I should say for some rational agents, standardizing mean differences does never omit decision-relevant information. This result doesn't come for free, though. We need to make assumptions both on the agent's utility functions and, more importantly, on the kind of measurement uncertainty the agent is allowed to have. And in particular, I want to highlight this assumption here, that this theorem assumes that the agent is certain they're dealing with quantitative measures. And we might think that's quite restrictive, right? Similarly, go back to this way of interpreting standardized mean differences, in which we assume that the measurement scores follow a normal distribution with the same standard deviation in the intervention and control group. Now, again, one can show that if this assumption holds, then for at least some agents, some rational agents, standardized mean differences always sufficiently inform them. But again, we need to both make assumptions here on the agent's utility function and on what kind of measurement uncertainty the agent is allowed to have. And again, the most important of which I want to highlight is that we assume in this theorem that the agent is certain that the property is measured on a quantitative scale, a cardinal or ratio scale. So again, we might think that's quite restrictive. In short then, there are scenarios in which, at least for some rational agents, standardizing mean differences does not strip away decision-relevant information, but at least as of now, these scenarios involve quite restrictive assumptions on the kind of measurement uncertainty an agent is allowed to have. Where does this all leave us then? So I think it leaves us here. So at a bigger picture question I have is that I want to ask, when should researchers standardize mean differences to inform evidence-based decision-making? And there are a variety of perspectives one can take on this question. The one I focused on today is the rational choice perspective. And from that perspective, I've argued that there are scenarios in which standardizing mean differences risk stripping away information that an agent cares about, and scenarios in which it doesn't. We should ask more generally, in which other scenarios do standardized mean differences not strip away decision-relevant information, sufficiently inform agents, and in particular, which other scenarios that are not quite as restrictive on the kind of measurement uncertainty. So for instance, we could try and relax the assumption on certainty about quantitative measurement and try to see if we can find scenarios in which standardizing them still never strips away decision-relevant information. And then, of course, we should ask, well, when do researchers and decision makers actually face these scenarios? And this will involve both philosophical discussion and empirical discussion. So on the philosophical side, we should, for instance, ask, well, when, if ever, are we justified in being certain about measuring a property quantitatively? That would be a philosophical question to discuss in this context. An empirical one would, for instance, be, well, when, if ever, or how often is data normally distributed? Or when are we justified in thinking that the standard deviation represents the same amount of a measured property? That's a partly empirical, partly philosophical question. Okay, and then overall, I think this would give us an answer as to when researchers should standardize mean differences to inform rational decision-making. And the answer, as is hopefully already clear, will be a quite nuanced one, which says standardizing is sometimes fine, but not always. And this deviates quite a bit from contemporary debates on standardizing mean differences that I didn't have time to speak about today. But basically, those debates proceed in an all or nothing fashion and say either never standardize or always standardize. And I think the recommendation we would get from pursuing this line of research I've been pursuing is something much more context sensitive. Okay, but I won't talk about this more for today. For today, I want to wrap up and just say this is what I've argued today. I've argued that standardizing mean differences risk stripping away information rational decision makers care about. And there are classes of scenarios, restrictive ones, but still some, in which for these some rational decision makers, standardizing mean differences never omits decision relevant information. And that's all for me today. Thank you. I'm not entirely sure I can hear you. Let me just, oh yeah, now I can hear you. So.
Many thanks, Ina. Let's take questions from the audience, if any.
If I may, I have a very very simple question. In all of your talk, you have been talking about sufficient information for the decision maker. How do you how can you say that some information is